Hello, my name is Sulin. In this video, I will introduce our paper Think While You Generate, Discrete Diffusion with Planned Denoising. This is joint work with wonderful collaborators, Juno, Andrew, Hannes, Yilun, and our advisors Tommi and Rafael. Diffusion models are built on the concept of generating data through an iterative process of noise removal. While they have achieved remarkable success in continuous domains like images, videos, and protein structures, recent work has aimed to adapt this framework for discrete objects. Typically, there are two main approaches of defining the noise distribution. You can either define the noise state to be a mask token, sometimes also called absorbing state. Here, the model progressively fills in the mask tokens with actual tokens in a random order. This process is closely related to any-order autoregressive models or masked language models, with autoregressive models representing a special case where the masking order is strictly directional. Alternatively, the noise can be defined as uniformly random. With this method, the denoising process begins with completely random tokens and iteratively refines them until the correct tokens are recovered. Theoretically, mask diffusion suffers from a limitation similar to that of autoregressive models, namely, tokens cannot be changed once unmasked. In contrast, uniform diffusion is thought to provide a more flexible and robust generative process by allowing multiple recovery paths for the correct tokens. However, in practice, mask diffusion consistently outperforms uniform diffusion when both are trained using the same computational resources. This trend is evident from early work such as D3PM to more recent studies like SED, and it has led to most of the latest research in discrete diffusion, focusing exclusively on mask diffusion methods. Motivated by these observations, a natural question arises. How can we unleash the true power of iterative refinement in discrete diffusion? In this paper, we address this by reformulating the generation process into two distinct steps, planning and denoising. We begin with the insight that the generation rate for each token during diffusion can be broken down into three components: a constant noise removal rate determined by the urgency at the current time, the probability that the token is corrupted, and the likelihood of successfully denoising it to the correct value. Based on this insight, we propose discrete diffusion with planned denoising, DDPD. Generation continues until the planner verifies that the entire sequence is correct, i.e., generation rate becomes 0 for all tokens. At each generation step, we simulate time until the next state transition. The planner first selects the token position to denoise based on its noisiness. Once a position is chosen, the denoiser refines the token. Here is an example of how the algorithm works on an MNIST generation example. Initially, the planner assumes all tokens are noisy and selects one uniformly at random for denoising. As the process continues, the planner identifies tokens that remain particularly noisy and prioritizes refining them. This iterative approach continues until the entire sequence is fully corrected. How do we train such a planner and a denoiser? Training objectives are very intuitive. You first corrupt the original data with random noise. The planner is trained to predict which one is noise, and the denoiser predicts the original token. In fact, theoretical analysis shows that these objectives naturally arise from decomposing the elbow. For the denoiser, it is also possible to use a masked denoiser by first masking out the noisy tokens and then making predictions. To recap, our plan and denoise sampler differs from the traditional denoise-only approach in three key ways. Instead of using fixed equal time steps, which can result in wasted steps when the time step is too small, we simulate the time step delta t until the next state transition. This ensures that every simulation step contributes meaningfully to the generation process. The planner selects which token or dimension to denoise based on predictions from a self-critic or verifier. This component assesses the current generation and identifies which token requires improvement, much like self-reflection or thinking behavior in autoregressive language models. With the token position chosen, the denoiser is dedicated solely to refining that specific token. This plan and denoise approach enables iterative refinement of the entire sequence, continuing until the planner verifies that the sequence is fully correct. In our paper, we demonstrate that integrating planning significantly enhances performance on GPT-2 scale language modeling and image token generation tasks. We also conduct ablation studies to show how each component of our sampler contributes to improved generative performance. For more details, please check out our paper and open source code.